welcome back to our channel Euclid Mathematics. We have started lecture series on CSIR NET SET Gate and other competitive exam too, like a complex analysis, ring theory, group theory, and other subject too in our channel. So if you wanted to see this video, you may check it into my playlist. Okay, so in my today's video, I'm gonna explain to you all one of the important question and topic from ring theory, which is a subring and their example. Okay, so let's get started on today's topic. I will explain to you all in detail subring and its some examples. Already we learn definition of a subring and a ring, all these things in my previous lecture. Now in my today's lecture, I will explain to you all some of the examples only. Okay, so we want the subring of a Zn. So subring of a Zn, already I explained Z1, Z2, Z3 and their subring. Okay, and we know that every subgroup is a subring. Okay, every subgroup gives subring. So we want the subring of Zn, and we know that subgroup of a Zn is a tau n. Okay, and tau n, sigma n. Okay, this concept I already explained in my group theory lectures. So subring of a Zn means we want the subgroup of a Zn, and always remember subgroup implies subring. Subgroup implies subring, but converse need not true. May be true or may not be true. So we cannot say about the converse, but every subgroup is a subring. So whenever you get the question to find the subring of our given ring, so you have to go through the directly subgroup, find out subgroup. It is the only subring. So if you are going to apply the definition, you are going to verify every element separately, it will be time taking. So this thing is not acceptable in your exam. So in your exam, what you need to do, you need to find out subgroup directly, which implies a subring. Okay, but if you want the subgroup, you do not have to go for subring. Converse, it is not there. Okay, and how we find the subgroup of a Zn? As to try to remember, subgroup of a Zn is a tau n. Okay, that means tau of n, we have to find the tau n for our given subgroup. Okay, given group, then we get the tau n. Okay, so for example, we want the tau of, let's find out some example. We want the subring of a Z12. Okay, we want the subring of Z12. So subring of a Z12 means subgroup of a Z12. Okay, and the number of a subgroup of a Z12 is a tau of 12. Okay, tau of 12. So how we find tau of a 12? So we take their to find out for tau 12, we use Euler phi function. Already we use the phi function for finding their value for P1, P2. Okay, so similarly we have to find out E1, E2 by using Euler phi function. Okay, so if you don't know how to find the subgroup, subring, and so many tau n, sigma n, Euler phi function, you may check my previous videos, it is already there. So tau 12 means divide 12 till we get the remainder 1. Okay, and tau 12, it says that, or tau n, it says that tau n, which is equal to E1 plus 1, E2 plus 1, E3 plus 1, and E4 plus 1, and so on. Okay, so how we find that E1, E2, or Euler phi function? We know that for finding phi n, v is 1 minus 1 upon P1 multiplied by 1 minus 1 upon P2 multiplied by 1 minus 1 upon P3 and 1 minus 1 upon Pn. So this is the way to find out the Euler phi function. Okay, this you need to know here. So tau n, we want the E1 plus 1, E2 plus 1, E3 plus 1, and so on. Okay, that means that tau 12 means E1 plus 1, E2 plus 1. And how we find E1, E2? So for 12, I divided 12 here till get the remainder 0. So we may see here the repetition of a number, first number, I represented E1 as a repetition of a 2 is a 2 times. Okay, it is a 2, and a repetition of a second number, it is only 1 time. So E2 1 I written here. So P1 is the number first, P1 is a 2 and P2 is a 3. So P1, P2 helpful for finding Euler phi function, and E1, E2 helpful for finding tau n. Okay, so here Z12 is equal to tau 12. Tau 12, I got the E1 2, E2 1. So E1 plus 1, E2 plus 1. Okay, so E1 2, E2 1. So tau n is equal to 2 plus 1 and 1 plus 1. So number of a subring of a Z12, which is 2 plus 1 is a 3 and 1 plus 1 is a 2. So 3 2s are 6. So number of a subring of a Z12 is a total 6. Okay, so we got the subring. Okay, we got the total number of a subring. How many subrings are there in our ring? But we want the which subring are actually exist. Which subrings are exist in our ring. Okay, so we want the subring. So if you wanted to find out the subring, you have to apply quite similar process like a subgroup. Okay, and what we have in a subgroup, in our subgroup we have Lagrange's theorem for finding subgroup. Okay, so order of a group divided by order of element, it says that a subgroup definition of a Lagrange's element of a subgroup, it says that. Okay, so order of element, so it is here we have to find out the element, which elements are divided to the 12. Okay, similar process apply here for the subring too. So 12 divided by these many elements. Okay, first 1, 2, 3, 4, 6 and 12, these numbers are divided by 12. Okay, and number of a generator, okay, number of a generator for our group, which is a divisor of a 12, so which are the total subring. Okay, so here, so one is a generator for whole group. Okay, one is a generator for whole group. It is a we say that 1, 2, 3, 0, 1, 2 up to 11, it generate whole groups in under Zn. Okay, Zn under addition we take. Or number of subgroup, we know that non-repeating generator, which is a number of subgroup. Okay, so that is a number of subgroup, and similarly apply for number of subring too. So one generator of our group, again similarly 2 is a generator of our group, 3 is a generator of our group. Okay, 4 is a generator. And if you don't know how to find the generator, so you check my previous video from group series, there I explained in detail how to find the generator of our group. Okay, so 4 is a generator of our group, 5 is again 6 is a generator of a group. Okay, so they generated 0 and 6 2 element. Okay, under Z12. So if you get under Z12 6, that means you will get the element 6. If you get the 6 to the 12, you will get the 12 under Z12 0, 18 under Z12 again 6. So you will get the repetition of the same number again and again. So you don't have to take their repetition. So you have to go for under Z12 writing their element, and under Z12 we have only the one element here, singleton 0. Okay, these are the total generator of our Z12. Okay, so how many subring we got it here? Total number of 6. And then they are namely as S1 generated by 1, S2 generated by 2, S3 by 3, S4 by 4, S5 by 6, and S6 by 12. These all are the total subring of our ring Z12. Okay. So similarly, find out for some other element. I consider here next Z49. Okay, Z49. So for finding the subring of a Z49, you have to find out the subgroup of a Z49, and the subgroup of a Z49 means tau of 49. Okay, tau of 49 means you have to find out it's a GCD till find the division till GCD is 1. Okay, we got the 7 7, E1 is a E1 2 times here, so E2 plus 1 is a 3. So I got the E1 as a 2, 2 plus 1 is a 3. So tau of 49 is a 3 here, which is namely as a subring of our ring Z49. So namely which subring exists there? So here we can see that divisor of 49, 1, 7, 49. Okay, these are the three divisor. That means ideal generated by 1, 0, 1, 48. This is also subring. So we want the 3 subring. Okay, so 1 into Z49. This one is the first subring. Ideal generated by 7. It can generate a group over ring. So ideal generated by 7 into Z49 is the second subring, and 49 is a singleton 0. Okay, so this is the third subring. So we have 3 subrings here. Okay, for our ideal generated by 1, 7 and 49. Okay, these are the 3 subrings here. So order of S1 we got the 1, order of S2 is a 7. Okay, and order of S3 is a, then we say that a Z49 has unique subring of order 7. Okay, so this is the only for our today's lecture. I wanted to explain here to you all, okay, the subring and subring of a Zn, how we can find, and their short formula, how can we find the subring using tau n. Okay, so I hope you all have understood my today's lecture. It is completely based on the subring of a Zn. Okay, so thank you everyone, thank you for my today's lecture.